The Technical Training Department of Yaskawa America Incorporated presents Medium Voltage Drive Basics. Welcome to Medium Voltage Drive Basics. In this session, we will explore the key technology and benefits of medium voltage drives. Now, before we get started, you may find it beneficial to view our related videos, Motor Basics and Drive Basics. Now, Motor Basics explores the construction, operating principles, and common applications of three-phase induction motors. Drive Basics introduces low-voltage variable frequency drives, their construction, how they work, and common motor applications that benefit from the use of drives. Well, many industrial and manufacturing industries rely on the use of electric motors, including oil and gas, water and wastewater, tire and rubber, mining, power generation, chemical, and cement. Variable frequency drives are often utilized for precision control of motor speed and torque and play an important role in improving system reliability and efficiency. Now, in this segment, we will explore medium voltage drives, a very specific subset of variable frequency drives. The majority of drives are low voltage drives, or LV drives. They typically operate on 240 volts, 480 volts, or 600 volt supplies, and drive motors from fractional horsepowers up to 1,000 horsepower. Medium voltage drives, or MV drives, provide a robust solution for the largest of motor applications. Typical applications operate at 2,400 volts, 4,160 volts, or 13.8 kilovolt supplies, and operate motors ranging from 500 horsepower up to 10,000 horsepower or more. MV drives are used on similar applications as LV drives, but on a much larger scale. Common applications include compressors, pumps, mixers, and conveyors. Medium voltage drives function much like low voltage drives. They may be programmed to provide volts per hertz, open loop vector, or closed loop vector motor controls using the same keypad and software interface as their low voltage counterparts. Now, you may be wondering, why medium voltage? What are the advantages of choosing an MV topology? How does a 1,000 horsepower medium voltage drive differ from a 1,000 horsepower low voltage drive? Well, how does it all work? In high power applications, MV drives have several advantageous characteristics. Now, the primary advantage is reduced current. The electrical power that a motor requires to satisfy an application is determined by multiplying the motor voltage by the motor current. Power equals volts times amps. Increasing the voltage allows the same amount of mechanical power to be developed with fewer amps. For example, to deliver 1,000 watts of power with a 1 volt supply, the system would need to deliver 1,000 amps of current. However, if the voltage is increased from 1 volt to 1,000 volts, the same 1,000 watts of power can be delivered with just 1 amp instead of 1,000 amps. Reducing amperage allows smaller conductors to be used, reducing copper and installation costs and reducing transmission losses. For a 1,000 horsepower application, 24 4-aught cables would be required to carry 1,200 amps on a 480 volt system. Medium voltage reduces the conductor requirement to 3 1-aught cables to carry 125 amps at 4,160 volts. The 24 low voltage conductors on the left deliver the same mechanical motor power as the 3 medium voltage cables on the right. Installation time and costs are reduced for both input and motor power wiring by using fewer and smaller cables. A second advantage of using MV drives is their ability to reduce motor inrush current at the start. When started across the line with a mechanical starter, starting motor current may exceed 600% of rated operating current. When generator or utility power system's capacity is limited, this starting current may result in severe voltage drop on the supply, impacting other connected equipment. Variable frequency drives avoid this problem by optimizing output frequency and voltage as the drive accelerates. When a motor is started with a drive, the current demand on the supply is a small fraction of across-the-line inrush current, avoiding voltage drops and utility penalties. As an additional benefit, drives provide nearly twice the starting torque when compared to starting across the line. A third advantage of MV drive multi-level topology is that it produces a nearly sinusoidal output waveform without additional output filtering. Using a drive with a sinusoidal output waveform reduces electrical and mechanical stress on the motor and increases motor reliability and service life. A clean sinusoidal output is also beneficial for applications that require long motor leads between the drive and the motor, and prevents the damaging effects of reflected waves on the motor wiring system. Now, this is especially important in applications like electric submersible pumps, where it is common to have a very long motor conductor between the drive on the surface and the downhole motor. A fourth advantage of MV drives is their ability to minimize harmonic distortion on the power supply, keeping the input waveform as clean as the output waveform. With smart harmonics technology, MV drives can achieve IEEE 519 compliance without additional harmonic filtering or mitigation. Minimizing harmonic currents and resultant voltage distortions reduces thermal stress on the power distribution system and can improve the reliability of all equipment on the power system. A final advantage of MV drives that we'll explore is their ability to synchronously transfer the motor from the drive to the power grid and from the power grid back to the drive. Because the input and output waveforms of multi-level MV drives are so nearly sinusoidal, like AC grid power, loads can be bumplessly transferred without interruption to the application. Now, before we dive into the details of how MV drives achieve these advantages, let's take a moment to review the basics of low-voltage variable frequency drives covered in the Yaskawa Drive Basics video. A drive is composed of three basic building blocks. The diode bridge converts AC line power to DC power. The DC bus acts as a bucket of power. Bus capacitors store the energy that the diode bridge pours in until it's needed. The output section is comprised of insulated gate bipolar transistors, or IGBTs. IGBTs are switches that turn on and off very quickly. The output section IGBTs draw energy from the DC bus and, through pulse width modulation, construct a three-phase AC waveform of variable voltage and variable frequency. Pulse width modulation, or PWM, is a process in which a controller varies the average output voltage by switching a higher voltage on and off at a high rate of speed. The IGBTs switch the DC bus voltage on and off thousands of times per second. The drive then arranges short pulses and long pulses such that the average voltage of the pulses approximates a sinusoidal waveform. By alternating which IGBTs are switching power, the drive can modulate a positive average voltage to motor leads U and V, or a negative average voltage to motor leads U and V. By sequencing all 6 output IGBTs, the drive can modulate an average sinusoidal signal to all 3 motor phases. The pulse width modulation controls the average voltage of the output. By varying the timing and sequencing of the output pulses, the drive can mimic the 60 Hz frequency of the line, decrease the output frequency to make the motor turn more slowly, or increase the output frequency to make the motor rotate more quickly. Using this method, low-voltage drives can approximate average sinusoidal output waveforms of varying voltage and frequency to achieve optimal motor performance. Multi-level medium voltage drives build on the same fundamental principles as low-voltage drives. Medium voltage drives are constructed with the same three basic building blocks, just more of them. The diode bridge converts AC to DC. The DC bus is the bucket of power that stores energy. And the IGBTs switch on and off, providing pulse width modulation. Modern MV drives utilize a cascaded H-bridge topology. The cascaded bridge topology allows for many modular power cells to be stacked, creating higher voltages and smoother waveforms. In the previous three-level low-voltage example, the drive can only switch 3 voltages to the output leads: the positive DC bus voltage, 0, or the negative DC bus voltage. A cascaded H-bridge connects multiple 3-level IGBT power sections in series. When 2 3-level bridges are connected in series, or cascaded, the result is a 5-level output bridge. In the 5-level cascaded H-bridge topology shown, the drive can switch 5 voltage levels to the output leads: the full positive DC bus voltage, half the positive DC bus voltage, 0, half the negative DC bus voltage, or the full negative DC bus voltage. Compared to the 3-level drive, 5-level drives create a waveform that more nearly approximates a sinusoid. The smoother waveform has many advantages, including less stress on motor windings and conductors, improved motor control, and reduced audible noise. So how does this magic work? A 5-level drive uses 2 3-level power sections, and this means that there are 2 independent banks of DC bus capacitors, and the output is switched by 2 independent sets or bridges of IGBTs. With 2 DC bus potentials and additional IGBTs, the drive may choose the level closest to the desired average output voltage. The drive can switch between 0 and half voltage, between half and full voltage, between full and back down to half voltage, from half voltage back to 0, between 0 and negative half voltage, negative half voltage and negative full voltage, negative full voltage back to negative half voltage, and then from negative half voltage back to 0 voltage, creating a stepped sinusoidal output waveform. Now that we've seen how a 5-level cascaded H-bridge may be used to create a smoother output waveform, let's build on that by connecting 2 5-level cells in series. The resultant output waveform now has 9 levels. Each time we add more switching levels, the output voltage steps get closer and closer to the ideal sinusoidal output waveform. Let's take a closer look at how 2 cells can be coordinated to create 9 voltage levels. Each 5-level cell can modulate positive or negative 1,000 volts or 2,000 volts. Connected in series, 9 voltage levels, including 0, can be achieved. The drive can switch between 0 and quarter voltage, quarter and half voltage, half and 3/4 voltage, 3/4 voltage and full voltage, half and 3/4 voltage, quarter and half voltage, 0 and quarter voltage, and continue the same steps with negative voltage. We created this 9-level single-phase waveform with 2 modular cascaded H-bridge drive cells. Since the output of these 2 cells is single-phase, we're not quite ready to drive a 3-phase motor yet. The next step is to combine 3 sets of cascaded single-phase output sections to form a single 3-phase cascaded output section. Connecting 3 sets of 2 cells in a Y configuration, we form a cascaded multi-level 3-phase Y output. Now, if it's easier to visualize, think of connecting the power cell outputs in the same way you'd connect 3 Y secondaries on a transformer to form a 3-phase Y output. With 6 cells connected in series Y, we can now create a 17-level 3-phase output. Each additional output level brings the waveform closer to the ideal sine wave. A smooth waveform reduces electrical stress on the conductors and motor insulation system. And because mechanical torque is created by current, a smooth waveform also provides consistent motor torque, reducing cogging vibrations that can cause mechanical wear and create audible noise. 3 levels of switching is coarse. 5-level switching is less coarse. 9-level switching is fairly smooth. With 17-level switching, the steps are so small that the result is nearly sinusoidal. Now that's a fine-looking waveform, but you might be wondering, how can the output waveform cause stress on the motor? Reflected wave phenomena can occur when the individual switched pulses from the IGBTs are reflected back on the line from the motor impedance. As the first pulse is reflected back, the potential can sum with the next incoming pulse, exposing the insulation system to as much as twice the bus voltage. Repeated exposure to high voltages will break down conductor and motor insulation, causing premature failure. Reflected wave still occurs with a multi-level output topology. However, because the voltage levels are a small fraction of the bus voltage, the potential reflections are also a small percentage of the total bus voltage and are typically safely within the rated limits of the motor insulation system. On a 3-level drive, reflected wave can increase the peak voltage seen by the motor to nearly 3 times the nominal RMS supply voltage. But with a 17-level output, the maximum peak voltage seen by the motor is limited to about 160% of the nominal RMS supply voltage, well within the tolerance of standard motor insulation systems. Well, we've explored how multi-level MV drive topology can improve system performance and reliability by improving the motor output waveform. So now, let's look at how choosing an MV topology can improve system input power quality. MV smart harmonic technology can be utilized to nearly eliminate the concerns of total harmonic distortion, or THD, present in 3-level drive topologies. What is harmonic current and where does it come from? Harmonic currents are created by the nonlinear switching of the diode bridge and occur at frequency multiples of the power supply frequency. The third harmonic of a 60 Hz system is 180 Hz. That's 3 times the fundamental frequency. The fifth harmonic is 5 times the fundamental, or 300 Hz. And harmonic currents don't contribute to beneficial mechanical work. We need to be cautious of harmonic currents because they do contribute to conductor heating, voltage drop, and voltage distortion that can adversely impact other equipment on the power system. In a typical low-voltage 6-pulse drive, current is only conducted when the sinusoidal supply voltage is greater than the bus voltage. This creates a rabbit ear waveform on each phase. One ear occurs when the L1, L2 voltage exceeds the bus voltage. The second ear occurs when the L1, L3 voltage exceeds the bus voltage. And the current waveform is nonlinear and does not resemble a sine wave. In a three-phase system, the diodes conduct at the top and bottom of each phase peak, creating 6 pulses per cycle. Multi-pulse transformers provide multiple phase-shifted three-phase outputs. Here is an example of a 12-pulse transformer's output voltages compared to a standard three-phase supply. As you can see, 2 sets of three-phase voltages are provided in the same period of time, essentially creating a 6-phase power supply. Instead of being 120 electrical degrees apart, the phases are separated by only 60 degrees. A 12-pulse drive adds additional diodes to take advantage of the multi-pulse transformer. By rectifying a second set of input waveforms, a second set of phase-shifted rabbit ears are also generated. When summed on the line, the 2 sets of rabbit ears overlap. The resultant waveform is more smoothly sinusoidal and is comprised of less harmonic content. The MV1000 medium voltage drive is comprised of 6 power cells, each connected to an isolated phase-shifted secondary, creating a 36-pulse drive input. 6 three-phase systems create 18 unique phase-shifted sinusoids. Each sinusoid charges the DC bus at the top and the bottom of the waveform for a total of 36 pulses per cycle. Just as a 12-pulse drive creates a smoother waveform than a 6-pulse drive, by summing 2 sets of rabbit ears, a 36-pulse drive nearly approaches a sinusoidal waveform by summing 6 sets of phase-shifted rabbit ears. The resulting current waveform contains negligible harmonic current content and exceeds industry guidelines for allowable harmonic distortion. We've examined how multi-level MV topology can be used to create grid-like sinusoidal motor waveforms while maintaining near-linear sinusoidal load on the supply. The power quality is so close to the 60 Hz grid that MV drives are able to smoothly transfer loads from drive control to line power and from line power back to drive control without interrupting the application. This is referred to as synchronous transfer. For example, a water utility may have periods of varying demand throughout the day. During periods of low demand, 1 pump may be required at partial load. During periods of high demand, 4 pumps may be required, each running at full load. Now, this is an effective solution. However, it may not be cost-effective to have a drive on each pump if they're only needed for peak demand. With synchronous transfer, a single drive can bring each pump online with a soft start ramp to limit the impact on the power system. When each pump reaches full load, the system seamlessly transfers the pump to line power and accelerates the next pump. As each pump is needed, the drive can provide speed regulation from 0 to full speed to exactly match the demand of the system and conserve energy. In a typical synchronous transfer application, an array of contactors is used to connect an MV drive output to the first motor. The drive is used to start the motor and can be used to regulate motor speed and torque operation. When full speed operation is required, the MV drive accelerates the motor to 60 Hz and synchronizes the drive output frequency with the utility supply frequency. When the voltages match, the drive closes a contactor to bring the motor on the line. For a few cycles, the motor is connected to both drive power and line power with no disruption to motor current or torque. Once synchronized, the drive opens a contactor to isolate from the first motor, leaving it running on line power. The drive may now close a contactor to connect to the second motor. The drive accelerates the second motor and synchronizes its output with the AC line. When the waveforms match, the drive simultaneously connects to line power. After transferring to the line, the drive can disconnect from the second motor and connect to a third. As load requirements are reduced, the process is reversed, and the drive seamlessly transfers the line-connected motors back to drive control, where they can be operated at variable speed or decelerated to a controlled stop. Unlike a contactor bypass application or open transition, synchronous transfer maintains uninterrupted motor current and smooth torque transfer. Medium voltage drives can be packaged for indoor use, general outdoor use, or to withstand the most extreme outdoor climatic conditions. While each application has a different look and different construction, each drive is comprised of the same basic building blocks. A multi-pulse transformer ensures clean power quality. Modular power cells provide precise sinusoidal motor control. A low-voltage control section provides an interface for control inputs and monitoring, and units may also be provided with optional switchgear to provide an integral means of disconnecting the medium voltage supply from the drive components. Well, in this session, we have introduced the basic construction of a multi-level medium voltage drive and explored how multi-level topology benefits power quality, both on the supply and at the motor. And now it's time for everyone's favorite segment, review questions. Review question number 1. When starting an MV motor, what advantage does a drive have versus an across-the-line start? The answer, inrush can exceed 600% of rated operating current when starting across the line. Using a drive allows us to increase the voltage and frequency over time to help reduce excessive current draw. Question number 2. How many voltage levels or steps does an MV1000 medium voltage drive have when measuring phase-to-phase voltage on the output? 17 levels or steps are achieved with 6 cells connected in series Y to form a 3-phase output. At Yaskawa, we do everything in our power to make each experience with us better than the last. Because to us, it's personal. To learn more about how medium voltage drives can benefit your application, visit yaskawa.com or contact your local Yaskawa representative. And thanks for watching.